In the previous chapters, chapter 16 and chapter 19, we have studied the static of the reactor behavior. In chapter 20, we are going to study the time-dependent reactor behavior. We are going to learn how the reactor will behave over the time. For the neutron population, the gain in the number of neutrons during a life cycle of time length L is defined as delta K equal to K minus 1. For example, if K is 1.1, then 1.1 minus 1 is 0.1. It means that after a certain time length L, then the neutron population is increased by 10%. Okay. Therefore, if at the beginning, if you have n neutrons, then after dt time, the gain of the neutron, dn, is equal to delta K times n times dt over L. And if the dt is equal to L, then you will have the increase of the neutron population, that is delta K times n. If delta K is 0.1, then you get 10% increase. So apparently this is a differential equation, and we can solve it. And the solution of this equation will be n will be this formula. And this inside this formula, the lowercase t is the time variable, and the capital T is a constant, which is equal to L over delta K. Okay, we call the capital T as a reactor period. And N0 is your initial neutron population, and this N is your final neutron population. And the next question is how to determine this L. Apparently, this L will affect how the neutron population will grow. So we have a typical lifetime LP for the prime neutron in a thermal reactor. And this LP is very short, approximately about 10 to negative 5 seconds. The prime neutron means that those neutrons are released right after the fission reaction. Okay. So the neutron is absorbed by the fuel, and the prime neutron is released almost instantly, so after relatively 10 to negative 5 seconds. If we consider the L as 10 to negative 5 seconds, then we consider delta K is a small value, and that is 0.02. For example, your K is 1.02. This will give a very short period of let me turn on my laser pointer. Okay. A very short period of 0.0005 seconds means that this neutron population will grow very rapidly. And the neutron lifetime in an infinite reactor, if the reactor size is very large and you have infinite size of a reactor, this neutron lifetime L infinity can be calculated from the velocity of the neutron V, and also the absorption mean free path lambda A. Okay. And we convert lambda A to 1 over sigma A, so we have this formula. And pay attention that here the V is the neutron velocity. Okay, it is not the mu we encountered before as part of the cross section. So this is the lifetime for infinite reactor. We also have the finite reactor. So the finite reactor will reduce this lifetime because the sigma A will be increased by this d times b square. So d will be the diffusion coefficient, and the bc square is the geometric buckling, as shown by this formula. So just the L times this non-leakage probability. Now let's calculate the example 20.2 for neutron lifetime. We have a certain large light water reactor. Then if it says it is a large reactor, means that the reactor is infinite, has infinite size, and we are calculating the R infinity. We also know the macroscopic cross-section for the water, so we know the sigma A. And we also know the temperature. We want to know at the 20 Celsius, what will be the neutron lifetime in this moderator. So from the previous equation shown here, we know that to calculate this R infinity, we need to know the velocity and also sigma A. The problem already gave us the sigma A, and the next step is to calculate the velocity. In nuclear engineering, the temperature and the velocity, they are related in this way. Okay. If we know the temperature, we are going to calculate the probable neutron velocity. So the most probable neutron velocity can be calculated in this way. So we have the KT. The K is the Boltzmann constant. Then T is the temperature. Okay, is equal to the kinetic energy of the neutron. So the kinetic energy is 1/2 mv squared. Then we solve for the V. Okay, solve for the V. Then V will be equal to square root of KT over M. Okay, square root of KT over M. So this relation is derived from the Maxwell formula. And this velocity, if the velocity is equal to square root of KT over M, then the Maxwell formula will give you the maximum value. And more detail can be found from chapter 2. Okay. So following this equation, we will calculate the velocity at a certain temperature. So K is Boltzmann constant. It can be found from the reference. And this Boltzmann constant has a different unit for different scenario. In this case, we are going to use the standard unit, so joule per Kelvin. Then we convert the 20 Celsius to 293 Kelvin. So 20 Celsius, that's room temperature. So that is 293 Kelvin. Divided by the mass of the neutron. So we are discussing the neutron, so the mass will be neutron mass. So this neutron mass in atomic mass unit, then times the conversion, we convert the atomic mass unit to kilogram. Then we get 2200 meter per second. This one means that at room temperature, 20 Celsius, the most probable neutron velocity is 2200 meter per second. It means that most of the neutron has this velocity. Okay. Then we solved for the velocity, and we will continue to solve the neutron lifetime. So follow this equation. We have 1 over 2200 meter per second. And because the macroscopic cross-section is given in the unit of centimeter, therefore we convert the meter per second to centimeter per second by multiplying 100. Then times sigma A, and we can get the result, which is 2.1 times 10 to the -4 second. And this value is extremely small. Okay. So if the reactor behaves very rapidly, we will not be able to control this reactor, because those small time frame, within that small time frame, we will not be able to use any mechanical device to regulate this reactor. That will not be possible for us to control it. So, fortunately, we have the prompt neutron. We also have the delayed neutron. So as shown here, most of the neutrons are released instantly. So we call it a prompt neutron. Okay, more than 99% of the neutrons are released instantly. However, a small percentage of the neutron, so about 0.65% of those neutrons, are released later, after a few seconds or after a few minutes, as a result of radioactive decay of a certain fission product. So we call those neutrons delayed neutrons. So if the neutrons are not released instantly, we call those neutrons delayed neutrons. Fortunately, with the delayed neutron, we can greatly increase this neutron lifetime and control the reactor. There are many different radionuclides that can give you the delayed neutron, but traditionally we say that there are 6 groups of radionuclide that will give you the delayed neutron with different decay half-life. The average rated half-life of the isotope can be calculated as 8.8 seconds for uranium-235, and the different fuel will give you different average half-life, and those values are around the same value. And we can convert the half-life to a mean life. A mean life means that after a certain time period, then this radionuclide will decay. So we can use this formula, tau is equal to half-life over log 2, and that is 12.7 seconds. It means that on average, the delayed neutron is released after 12.7 seconds after the fission. The 6th group and their fraction are listed here, and their half-life in seconds are also listed here. Okay. So if we do a summation of all the beta I, the value is about 0.0065. Now let's define the beta T as the total delayed neutron fraction. And that is a summation of all the beta I in the previous table. For uranium-235, this value is 0.0065. Then if the beta T is the fraction of the delayed neutron, then 1 minus beta T will be the fraction of the prompt neutrons. And the prompt neutron take a very short time LP to appear, which is about 10 to negative 5 seconds. Whereas the delayed neutron take a much longer time, that is LP plus tau, to appear. And the tau is 12.7 seconds, which is much larger than LP. The average delay, R effective, can be calculated by this formula. Here you have the prompt neutron fraction times prompt neutron lifetime plus delayed neutron fraction times delayed neutron lifetime. You can cancel negative beta T times LP, cancel this part with this part. Then you only have the LP, 1 times LP, you get LP plus beta T times tau. Then LP is much smaller than the beta T times tau, so we have the final beta T times tau as your R effective. We can calculate this R effective, which is equal to 0.083 seconds, because the beta T for the fuel is 0.0065 and tau is 12.7 seconds, okay, for uranium. This value greatly exceeds the multiplication cycle time, which is only 10 to negative 5. So that we will allow us to control the reactor. Now let's take an example to show you the importance of the delayed neutron. We consider the delta K to be 0.001, okay, very small change in the K. And our effective is 0.083 seconds. The reactor period, T, can be calculated from our previous equation, our effective over delta K. In that case, this reactor period is 83 seconds. Now we are going to calculate what will be the neutron population after 1 second if you have the K that is slightly above 1. So we use our previous exponential formula. Nt is equal to n0 times this exponential factor. We replace the lowercase t as the 1 second and replace the capital T as 83 seconds. So we can find that the neutron population is increased by 1% after 1 second. Now, for comparison, if we consider only the prime neutron, so we remove all the delayed neutron. In that case, the reactor period T is equal to Lp, prime neutron lifetime, which is 10 to the negative 5 seconds, over the same delta K. We get 0.01 seconds. Then, after 1 second, you will see that the neutron population have been multiplied by a very huge number. In that case, the reactor behave very rapidly and we will not be able to control it. Previously, in the previous example, we used a very small delta K. In that case, we found out that the reactor power or neutron population increased slowly. On the other hand, if your delta K, which is approximately equal to the reactivity rho, if your delta K or rho is greater than beta, means that you have a higher multiplication factor or much higher reactivity insertion into the reactor. We can still get a very rapid response, even with the delayed neutrons. As shown by this figure, you can see that if you have a delta K that is small, that is 0.1 beta, you have a very slow reactor power increase. With the increasing of this delta K, you will see that reactor power increase rapidly. Okay. And we can use this formula to estimate the reactor period. If your delta K is smaller than the beta T, then we use this formula. If the delta K is larger than beta, we use this formula. So the beta will be the boundary between the slow response and rapid response. Therefore, the reactivity is often expressed in terms of dollars, okay, dollars and cent, like US dollars and cent, by taking the ratio rho over beta T. So $1 means that the reactivity is equal to beta T. If the problem says that there is $1 reactivity insertion, then this rho is equal to beta. Then for the uranium-235, this beta will be 0.0065. Then apparently, then 1 cent is 1 over 100 beta T. In addition, we will also use another unit to describe the reactivity. So this unit is called the PCM, or percent millirho. So milli is 10 to the negative 3, then multiply 1%, 10 to the negative 2, so that is 10 to the negative 5. So 1 PCM is equal to 10 to the negative 5 reactivity. Okay. Because the reactivity is normally a small value, therefore we artificially define this small value to describe this reactivity. Now let's move to the example 20.4. Now we have 2 cent of negative reactivity insertion. So rho is equal to 2 cent. The negative 2 cent is introduced into a critical uranium-235 reactor operating at 150 megawatt thermal. Calculate the reactor's thermal power after 5 minutes. 2 cent is much smaller than $1. Therefore, we can say that this reactivity rho or delta K is much smaller than beta. Therefore, we use this formula to calculate the reactor period, which is the first formula in the previous slide. We replace this rho by 0.02 times beta. So because it is 2 cent, so that is 0.02, then times beta. It is negative, therefore we have this negative sign here. Then the beta t will be cancelled, and we have this negative 635 seconds for the reactor period. After 5 minutes, the reactor power can be calculated from the same exponential function. Because the neutron population is proportional to the power, therefore this formula is also applicable to the reactor power. After 5 minutes, we have the P0, that is 150 megawatt initial reactor power, times negative 300, because that's 5 minutes, so 5 times 60, you get 300, over negative 635 seconds. So we get a 93.5 megawatt thermal. So it means that you have a negative reactor reactivity insertion, so the reactor power is decreasing. After 5 minutes, the reactor power is reduced to 93.5 megawatt thermal. We can further extend this problem, and if the beta is equal to 0.0065 for a typical light water reactor using uranium-235, then we can calculate the reactivity, the actual value of this reactivity. The actual value of this reactivity insertion is rho, that is equal to negative 0.02 beta, which is equal to this value. This corresponds to negative 13 PCM. Okay, this times 10 to 5. In this slide, I will introduce the important reactivity feedback concept. So some of the feedback is positive, some of the feedback is negative. For positive feedback, it will accelerate the initial change to the system. And for the negative feedback, it will try to mitigate the initial change to the system and return to its original state. For positive feedback, for example, you have an apple on the tree. The apple is ripe. A ripe apple will release acetylene, and the acetylene will cause the surrounding apple to ripen as well. Then you have more ripe apples, you have more acetylene, then eventually all the apple ripen. So this is an example of positive feedback. It will accelerate the initial change to the system. For the negative feedback, there's another example. If you are running, your body temperature is going to increase, and you are going to sweat. Then the evaporation of the sweat will absorb your body heat and reduce your body temperature. This is an example of negative feedback, because our body tries to maintain constant temperature. For the reactor, we want the negative feedback because if the for certain unknown reason, if there's any power change, power increase, power surge, we want the reactor to be inherently safe and automatically reduce its power. In general, there are two reactive feedback mechanisms. One is the field, another one is moderator. And for the moderator, it has two effects. It can give you either negative feedback or positive feedback. First, if the moderator temperature increases, then the water is going to expand, and you are going to have a reduced density. If you have a reduced density, you are going to reduce your moderating ability. In that case, you have less thermal neutron produced, and that will reduce your multiplication factor and reduce your power. So that is the negative feedback. In the moderator, normally there are dissolved boron. Boron is a neutron absorber. Then if the moderator expand, you also have a less boron concentration. Then less boron means that you have less neutron being absorbed. In that case, you have a positive feedback because less neutron is absorbed, then more neutron can be used to trigger the fission reaction. In general, if the reactor is over-moderated, you have more water per field pin, the moderator temperature feedback is positive. If your reactor is designed in a way of under-moderated, in that case, the moderator temperature feedback will be negative. Therefore, for commercial reactor, we normally design the core to be under-moderated. Okay. For the field, it will give you the negative feedback. This is due to the Doppler effect. As shown by this figure, you will see that at 0K, you have very narrow and tall capture cross-section peak. Okay. And with the increasing of the temperature, this peak is lowered and also widened. In that case, you will get the negative feedback because the neutron will be absorbed more when it is moderated, when it is slowed down inside the field. Now let's use the alpha to represent this reactivity feedback concept. The alpha is called the temperature coefficient. Ideally, this alpha is negative, but for certain systems, the alpha may be positive. Then your reactivity rho can be calculated as rho is equal to alpha times delta T. And we have another relationship, so that the alpha is called alpha P. The alpha P and the alpha, they are not the same value. The alpha P is used with the change of the power. However, for the alpha is used for the change of the temperature. Let's use an example to show how to use this alpha. So we have a value of this reactivity feedback coefficient, alpha, that is equal to negative 10 to negative 5 per Celsius. And we have a temperature rise of 20 Celsius. And for 20 Celsius, we use the 20 times this alpha. You get negative 0.002. You see that you have a temperature rise, but you get the negative reactivity. means that the reactor power will automatically be decreased in order to help to reduce the system temperature. Here, the temperature rise, that is positive 20 Celsius. If you see the temperature decrease, then this temperature delta T should be a negative value. In that case, you have the temperature drop, then you have the positive reactivity insertion. So the system power is going to automatically increase a little bit so that the system temperature will go back to its normal set point. Next, we get alpha P. If the alpha P is equal to this value, pay attention that this alpha P will have no unit because the alpha P is going to be multiplied by a power ratio which has no unit either. Then we have a 2% change in the power, okay, 2% increase of the power. Then your reactivity will be equal to this value, following this formula, alpha P times delta P over P. Delta P over P is 2%. Then you get again a negative value. Means that you have a certain power surge 2%, then you automatically get the negative reactivity, and your power is going to automatically decrease and return to its original set point. In the real world, the reactor is controlled using different methods. The first one is by introducing the boron content into the coolant or into your moderator. Because boron is a neutron absorber, by introducing the boron into the coolant, you can absorb neutrons. You have more boron, then you can reduce your reactivity more. This is called the chemical shim. This one can balance the excess fuel loading, and it is adjusted gradually as fuel is consumed during the reactor life. So at the beginning, your fuel concentration is higher, you add more boron. At a later time, your fuel is burned a little, then you can reduce this chemical shim a little bit in order to control this reactivity. In addition, we can also install the burnable poison rod into this fuel assembly. Those burnable poison is made of boron carbide or gadolinium. Both boron and the GD, they are neutron absorber, and they can burn together with the fuel. So the fuel is burned, so the fuel enrichment is reduced over the time, and the amount of this burnable poison is also burned, so that they have a very good balance over the lifetime of this fuel. In addition, the reactor also controlled with several groups of movable rod. That is called the control rod, as shown by this figure. And those control rods can be controlled by the operator sitting in the control room. So those control rods are inserted from the top for the pressurized water reactor, and actually they can be dropped into the core using the gravity. However, for the boiling water reactor, the control rods are inserted from the bottom, because on the top, the boiling water reactor must use the moisture separator. The negative reactivity inserted to the core or the integral control rod walls can be calculated by this formula. And this formula is a function of the insertion depth Z only. You can see that you have your variable Z here and also your variable Z here. This rho T is the total worth of this control rod, means that what will be the total reactivity insertion if you insert this control rod fully into the core. And Z is between 0 and H. So for Z is equal to 0 means that the rod is completely withdrawn. In that case, you have a 0 minus 0 inside this bracket, then you have the reactivity insertion 0. And if the Z is equal to H, then you have H over H, that is 1 minus sine 2 pi, which is 0. Then you have the rho H, that is equal to rho T. Okay, means if the rod is completely inserted, you will get the rho T. In this figure, it shows the solid line is the integral control rod worth. So at the beginning is 0, and when the rod is fully inserted, you have the all your control rod worth. The dashed line is the differential worth. That is the amount of reactivity introduced per unit distance of control rod movement. You will see that this value is high at the center, because at the center you have a highest neutron flux. Okay. And it means that the control rod is more effective when it is reaching the center of this core. Now let's look at this example, 20.6. So we have a cluster of control rod. It has a total worth of $1.5. Yeah, $1.5. And the control rod, which are initially positioned 35% into the core, are moved to a depth of 42% of the full insertion. We'd like to calculate how much reactivity was introduced by this movement. So you are going to insert this control rod deeper into the core. So the change of this reactivity delta rho is equal to initial reactivity minus the final reactivity. So the initial is 35% of the H. Okay, so 0.35 times H minus the rho final, that is 42% of the H. Then we further expand this equation using the formula introduced on this slide. Then the H will be cancelled. Okay, H will be cancelled, and you will get a value for the first bracket and another value for the second bracket. Then you will get this result, and that is negative $0.18. Means that you insert this control rod deeper into the core, you will get additional $0.18 of this reactivity. So as shown here, a deeper insertion of this control rod result in a negative reactivity change to the core. So the total control rod reactivity worth can be estimated by this rod drop technique. So if we drop this control rod into the core from the fully withdrawn condition to fully inserted condition, it will rapidly reduce the neutron flux in the core from phi 0 to phi 1. Okay. And by measuring this phi 0 and phi 1, we can calculate this reactivity worth of this rod using this formula. So rho over beta is equal to phi 0 over phi 1 minus 1. Now let's talk about the fission product poisons. The fission product, also called nuclear waste, is the remaining part of the fuel. So after the fuel is fissioned, it will become the fission product and stay inside this fuel region. So after the fuel is burned, the fission product will build up inside this fuel. those fission products will absorb the neutrons. Then if the neutron is not absorbed by the fuel, it will reduce the neutron economy. Some of those fission products absorb lots of neutrons, means that they have a very large absorption cross-section. The most important fission product poison is the xenon-135. It has a cross-section of 2.65 million barns, which is huge. And another one, samarium-149, also has sigma A, that is 41,000 barns. Okay. When they are inside this reactor, they are going to reduce this K. So this xenon-135 is generated directly from the fission as well as from the decay of Te135 and also Ldam-135. And means that the fission reaction can produce xenon-135 directly, and some other fission product decay can also produce this xenon-135. This xenon-135 during normal reactor operating condition, you have a large quantity of neutrons. Those xenon-135 can be burned, so you get the balance between the fission and also the absorption by this poison. However, after the reactor is shut down, then this xenon-135 began to accumulate inside this reactor. And in that case, if the reactor is shut down, you cannot restart the reactor quickly because you have a large quantity of this fission product poison inside the core. If you want to restart the reactor quickly, you have to withdraw lots of control rod and make this reactor very unstable. The normal way is that you wait a couple of days until this xenon-135 decay out, then you can restart your reactor. The next section is fuel burn up. In this section, we are going to study how the reactor will change after the fuel is burned. So the reactor power is proportional to neutron flux according to this equation. In this equation, the P is the reactor's thermal power. The phi is the average neutron flux. NF is the total number of fuel atoms. Sigma F is the macroscopic fission cross-section of the fuel, and W is the average heat released per fission. Okay. Then, if the fuel is burned, you are reducing the NF. You are reducing your NF. To maintain the same power, you have to increase your neutron flux. So it means that the reactor that experiences the fuel consumption, the flux must increase with time in order to maintain the same level of the thermal power. Now let's look at an example. For this example, we'd like to examine the fuel utilization in a simplified pressurized water reactor that use 20 weight% fuel and operate at 100 megawatt E or 300 megawatt thermal, as in a test reactor or a propulsion reactor. The reactor power is 300 megawatt thermal. The initial fuel loading to a single zone is 1,000 kilogram uranium. Determine the fuel enrichment after 1 year of operation. Okay. So we have a 300 megawatt thermal, and it is operated for 1 year. We are going to calculate the fuel enrichment after 1 year. First, we'd like to determine to produce 1 megawatt day of thermal power, how much fuel is burned. We can calculate the number of joules inside the 1 megawatt day. So 1 megawatt day means 1 megawatt thermal power operated for 1 day. That is 1 megawatt 10 to 6 watt times 24 hours times 3600 seconds per hour. So we get this value. That is the number of joules in 1 megawatt a day. And to obtain 1 megawatt a day energy, the required number of fission reactions can be calculated in this way. And we know that each fission releases 190 MeV recoverable heat. Then we can simply calculate how many fission reactions are needed. So we use the total amount of heat over 190 MeV. Certainly we need to convert 190 MeV to joule. Then we get this number of fissions. Each fission reaction will burn 1 uranium-235. Okay. Therefore, to produce 1 megawatt a day, it will consume this number of uranium-235. We also know the mass of the 235 fuel atom, which is 235.04 gram per mole. So we use the number of fuel atoms burned divided by the Avogadro number. We get a number of moles of this fuel that is burned. Then we times the atomic mass. We can get the mass of the fuel that has been burned to produce 1 megawatt a day. Or to produce 1 megawatt a day, thermal power about 1.11 gram of the uranium-235 is burned. It undergoes fission reactions. However, the total amount of the 235 that is consumed will be higher than the previous value, because some of the 235 will absorb a neutron without fission. Means that the neutron is consumed by 235 and 235 is consumed, but you don't get any fission energy. This effect can be estimated from this table. In this table, you'll see that you have a capture cross section, which is not zero, means that there's a certain fraction of the neutron absorbed by the 235 without giving you the fission. And then we will use the following equation. We use the following equation to calculate the actual 235 that is consumed. We use the previous value to multiply sigma A over sigma F, because the previous value only considered the sigma F. Now we will also consider the sigma A. Sigma A is the summation of the sigma gamma and sigma F. Okay. Now we get a new value. This value, you can use this value directly, and it is the amount of the mass of the 235 that is consumed to produce 1 megawatt a day. So to produce 1 megawatt a day, 1.295 gram of the 235 is consumed. Therefore, in 1 year, the amount of 235 that is consumed can be calculated using this formula. M consumed is equal to 1.295 times the total number of megawatt a day. So you have 300 megawatt thermal times 365 days. And you get 142 kilogram of the fuel that is consumed. And at the same time, we can also calculate the amount of the uranium-235 that is burned or undergoes fission reaction. We use the 1.108 as the factor, then times the same number of megawatt a day, we get 121.3 kilogram. Just pay attention to the wording And the book uses the word consumed, that is, the total amount of the 235 disappeared inside your reactor. Then if it asks for something that is burned, means that it only consider the fission reaction. Okay, only consider the uranium-235 that is fissioned. The calculation is not finished because the problem actually asks for the new field enrichment. By definition, the field enrichment is the mass of the 235 over the mass of the total uranium. That will include all the uranium, 235, 238, and all other uranium isotopes. So after 1 year, the fuel 235 is reduced by the MC, that is the total consumed. If the fuel became anything else, we will remove it from the fuel content. That is, so the total remaining fuel mass will be the initial fuel mass, that is 1,000 times 20% minus the MC. MC was previously calculated, over the total amount of the uranium left inside the core. Here, if the uranium-235 undergoes the capture reaction, it will become the uranium-236. Uranium-236 is still uranium. Therefore, when we are calculating the denominator, the total amount of the fuel, total amount of uranium, we will use the initial total uranium 1,000 kilogram minus the fuel that is burned. Okay, means minus the mass of the 235 undergoes the fission reaction. So pay attention to this difference, MC and MB. Then the result will be 0.066, means that the fuel enrichment is reduced from 20% to 6.6% after 1 year of operation. At the same time, we can also calculate the electricity. So electricity, that is PE, which is 100 megawatt. And we convert the 100 megawatt to kilowatt because electricity is normally measured in the unit of kilowatt hour. Then in 1 year, 365 days times 24 hours, you get a number of hours. Then the result will give you the number of kilowatt hour. In a real reactor, the fuel assembly are grouped into several zones. Each zone will have a different fuel enrichment. In this figure, you can see there are two different arrangement of the fuel. In the left figure, you have the lowest enrichment of the fuel at the center, then the highest enrichment of the fuel at the boundary. This configuration will give you a relatively flat power distribution. At the boundary, you get lower neutron flux, but you get a higher enrichment, so you get relatively the same power. At the center, you have a higher neutron flux, but lower field enrichment, so you have the same power. Alternatively, you can also have this checkerboard arrangement. So the reactor is shut down periodically to remove some of those fuel assembly, then rearrange the rest of the fuel assembly and also install the new fuel assembly. So each operating period, or we can call it a fuel cycle, typically lasts from 18 to 24 months. And during the refueling period, the engineers will replace roughly 1/3 of the fuel assembly and rearrange the rest of the fuel assembly with the new fuel assembly. then the reactor will be restarted again for the next fill cycle. From the previous study, we know that at the beginning of your fill cycle, you have excess of the fuel, means that the fuel is more than you need. Therefore, the reactor must be supercritical, unless you have some other compensating measure to reduce its reactivity. In this pressurized water reactor, this excess fuel reactivity is compensated or reduced by the inclusion of the control rod, boron solution, and also the burnable poison rod we introduced before. Over the time, the fuel will gradually begin to burn out, so the fuel concentration is going to decrease. At the same time, the concentration of the boron is also reduced. By the end of the cycle, this extra fuel is all burned. Then all the available control absorption will be removed as well. Then the reactor will be shut down and ready for the refueling. So this will complete one reactor fuel cycle. The example 20.9 shows the concept of the parts per million. So that's the ppm. If the fuel is expected to go from 3% to 1.5%, so this sentence is irrelevant to this question. Okay. So we have an initial boron atomic number density in the moderator that is approximately 0.001 times 10 to 24 atoms per cubic centimeter. For comparison, the number of water molecules per cubic centimeter is 0.0334 times 10 to 24 molecules per cubic centimeter. Then the boron content is usually expressed in parts per million, ppm. For example, microgram of an additive per gram of diluent. With 10.8 and 18 as the molecular weight of boron and water respectively, we'd like to calculate the boron concentration. So the boron concentration is defined as the weight of boron over the weight of water. Okay. Then we can expand the weight of boron in this way. We have the number of moles then times the molecular weight. So the number of moles can be calculated as the total number of molecules or atoms over the Avogadro number. The total number of atoms is the number density times the volume. Okay. The NB is this value, 0.0001 times 10 to 24, times the V, that is the moderator total volume, then over the Avogadro number, you get a total number of moles, then times the atomic weight, that's mass per mole, you get the total mass. In the denominator, the same, that is for the water, total mass of the water. So the water number density, water molecule number density is also given, times the same moderator volume over the Avogadro number, then times the molecular weight of the water. Then apparently the Avogadro number, Na, and also the volume of this moderator, they are both cancelled. So you have only Nb over Nw times Nba over Mw. Then you put those numbers into this formula, then that factor 10 to 24 will also be cancelled. Then you will get this value. So this result, that is the mass fraction for the boron. Okay, mass fraction for the boron. Then we will multiply this value by a million. Okay, multiply this value by 1 million to convert this fraction to ppm. Okay. So this is just the concept of the ppm in the scenario of a nuclear environment. The last knowledge of this chapter will define the specific burn-up. The total thermal energy E extracted from the initial uranium mass, Mu, including all the fissionable isotope, is the specific burn-up expressed as the number of megawatt days per metric ton uranium or heavy metals. So the unit will be heat per metric ton of uranium. So the heat is expressed in the unit of megawatt day. So this fuel burn-up B is equal to the total energy extracted E over the initial uranium mass, Mu. Now let's use the example 2010 to show how to calculate this specific burn-up. We can calculate the burn-up value for 1 year of operation of a 3000 megawatt thermal power reactor with an initial uranium-235 fuel loading of 2800 kilogram. And the initial enrichment is 3%. Then, from this 2800 kilogram of 235, we can calculate the total amount of uranium, including both 235 and 238. So we use the 235 fuel mass over the 3%. So we get a 93,000 kilogram or 93 tons. Okay. This 93 tons is the Mu, that is your initial uranium mass, including both the 235 and also 238. The total heat produced within a year is 3000 megawatt, thermal times 365 days within a year. So the result will automatically in megawatt day. Then by definition, if we discharge this fuel after 1 year, then the burn-up is equal to the total heat produced in megawatt day, so that is 1.1 million megawatt day, over 93 metric tons. So we get 12,000 megawatt day per metric ton. This will conclude the chapter 20.